I'm Chuck Newell with GSI Environmental.
And I'm Dave Adamson, also with GSI Environmental. This is one of a series of videos that highlight cutting-edge CERDP and ESDCP R&D efforts.
Now today we're talking about an emerging contaminant, 1,4-dioxane, and learning about how it behaves in groundwater.
That's right, Chuck. So let's take a look at what we'll cover in this video. 1,4-dioxane is a relatively new addition to our monitoring programs at contaminated groundwater sites. And the problem is there's not a lot of empirical data on how it behaves in the environment. So if your job is getting a site cleaned up, you don't have as much information to rely on.
Now, this was part of a focus of a CERDP-sponsored project titled In Situ Treatment and Management Strategies for 1,4-dioxane Contaminated Groundwater. Now, Dave, I know you're the PI in the project, and I've also been working as co-PI, along with a great group of researchers like Dr. Shelley Mahendra at UCLA, Dr. Michael Wong at Rice University, and Dr. Dan Bryan at Woodward Curran, formerly at GeoCleanse.
Now, the overall objectives of this particular project were to build a better conceptual model for how 1,4-dioxane behaves in the environment so that we have a more informed basis for managing these sites. And this was accomplished through a combination of big data studies, lab-scale treatability tests, including ones involving treatment trains, and collecting field data at dioxane-contaminated sites.
Now, we can't cover everything from this project today, but here are a few of the key points that we're going to discuss. First is that there's a lot more evidence for shorter plume size than maybe we had feared based on dioxane's properties.
And second, there's more evidence for attenuation of dioxane relative to what we may have anticipated.
And finally, other processes like matrix diffusion should be accounted for when trying to manage these sites. In short, we've just got a much better conceptual model than when we started. So let's take a closer look at 1,4-dioxane to help define the nature of the problem. As a groundwater contaminant, it's a big deal because it was used as a stabilizer for 1,1,1-trichloroethane. Right, Dave?
Yeah, that's right. Now, I've got some of the structures of the relevant compounds sketched out here. How about a little quiz for you, Chuck? What's that first compound there?
Okay, let's see if I can do this. Well, that's the big guy. That's 1,4-dioxane, the subject of our video here. And then we've got a 1,1,1-trichloroethane in the middle.
And we've got that included here because 1,4-dioxane, again, was often added to 1,1,1-TCA, so they'd be expected to co-occur. And how about that third compound?
Okay, and that's an also chlorinated solvent, trichloroethane.
Exactly, 3 for 3 on the quiz. TCE is important because it may have been the first solvent used at a lot of these sites. And then, there was a switch to phase out TCE due to occupational health concerns, but then maybe a shift to 1,1,1-TCA. A lot of these sites then where chlorinated solvents and their degradation products are present, there'd be a strong likelihood that dioxane is present too, and we've got a lot of data to prove that. Dioxane, of course, presents several problems. First, it may not have been included in the monitoring program yet, and it has always been considered pretty persistent as well.
Right, and it's also highly soluble in groundwater while not strongly sorbing to aquifer material.
So that's led to a concern that at sites where a chlorinated solvent plume is formed, there may also be a dioxane plume that's been racing out ahead and creating a much longer plume.
So that's one of the hypotheses that you wanted to test, and then you used actual monitoring data to figure out what was happening at these sites, right?
Yeah, and we performed a big data study using databases like the GeoTracker database out of California. And what we did was develop a method to estimate relative plume sizes for just over 100 sites with dioxane. I think the easiest way to show what we found was to go back to that cartoon of co-occurring plumes.
And then let's take a look. What percentages for the dioxane sites fell into the category you already drew, where the dioxane plume was longer than the chlorinated solvent plume?
Well, this was the case that we assumed would be the most common, but it turns out that only 21% of the dioxane plumes were demonstrably longer, far from the majority that we'd expected. At another 23% of the sites, the dioxane plumes were about the same size as the chlorinated solvent plume.
Now, I think I can do the math, so that means that the remaining 56% of the sites was actually the chlorinated solvent plume that was longer than the dioxane plume. Definitely different than what we'd expect based on dioxane properties. What gives? What happened?
Well, for the most part, it was 1,1-DCE and TCE that were longer, not TCA. And remember that TCA is attenuated fairly quickly. TCE, which might have been the first chlorinated solvent used at these sites, that would give it a couple decades head start if that dioxane was really associated with TCA releases. And, dioxane plumes have the chance to catch up, but at least right now what we're seeing, most of them are the same or shorter in terms of plume size.
Okay, so that's plume size, an example of the scale of the problem. Now let's take a look at dioxane attenuation. What did you find out?
Well, we teamed up with Hunter Anderson at the Air Force, another expert in 1,4-dioxane, and we were looking at attenuation in a couple different ways. So first, we estimated source attenuation rates at all of the geotracker sites and determined which ones of these were statistically significant. That's what's shown in this histogram with the frequency distribution of the dioxane half-lives on the y-axis.
Okay, and then you did the same thing with the Air Force data?
Well, Hunter did the analysis of the Air Force data, and he was using monitoring well data instead. But in both cases, we were able to establish that significant dioxane attenuation was occurring at a meaningful number of locations. Certainly not at every site. That's because we had to set some statistical thresholds, so that knocks out a lot of sites with short monitoring records. But we were able to establish that on a site-wide basis, the median dioxane half-life was 20 months for those 22 sites. And on the individual wells on that right panel, the median value for these 131 wells, that corresponds to a half-life of 48 months. And these are meaningful half-lives if you're considering site management with natural attenuation, which you might be interested in over the course of a decade or more.
Now, know that you also looked at about how dioxane attenuated relative to chlorinated solvents at these sites as well.
And it turns out for the geotracker data, the dioxane attenuation rate tended to be similar to the attenuation rates for TCE and 1,1-DCE, or at least difficult to distinguish statistically. The TCA rate, that was typically much faster, which matches what we'd expect.
So the bottom line is that dioxane rates were not that different than several of these important co-occurring contaminants, right?
Yeah, and one other important point to make is that dioxane attenuation could be positively correlated to the presence of oxygen and negatively correlated to high concentrations of chlorinated solvents and metals. And now these are the same conditions that we'd expect based on all the great work that's been done at Rice University, UCLA, and other labs, where they've shown that these are important parameters for biodegradation. For example, the presence of oxygen is important because all biodegradation pathways identified to date are aerobic, not anaerobic. Shaili Mahendra at UCLA has demonstrated that the presence of 1,1-DCE and several other chlorinated solvents inhibit these biodegradation reactions. And inhibition is also noted with elevated levels of metals such as cadmium or copper. So our field evidence from this project is definitely consistent with the lab evidence and suggests that biodegradation is also playing a role at the field sites.
Wow, I think that's really an important point, that there's evidence that biodegradation is a viable way to treat 1,4-dioxane plumes. This is another area where we're changing that old conceptual model for 1,4-dioxane.
Right, and remember, these lab studies, they've isolated aerobic organisms that can degrade 1,4-dioxane as a carbon source, as well as organisms that degrade it co-metabolically in the presence of a co-substrate like propane. For treatment, this ends up being important in a couple different ways. First, the potential for natural attenuation can be assessed because there's these biomarkers for those organisms, and they can be measured in environmental samples. So that gives you a strong line of evidence for M&A. Secondly, it points out that enhanced bioremediation using amendment injection or even bioaugmentation may be an option at some sites if there's a need to speed up mass removal.
Now, it's not going to be the same design that works for chlorinated solvents, which mostly degrade anaerobically, but maybe it's an add-on, like what's shown in this cartoon. This is a sequential anaerobic, then aerobic in situ treatment process.
Yeah, that's one way to do it. Another option that this project was looking at is in situ oxidation to treat the chlorinated solvents, followed by bioaugmentation in the same aerobic conditions. We've shown that these dioxane degraders do great as a second step, and that this is a treatment train that could be effective for 1,4-dioxane.
Okay, in terms of plume footprints and the potential for attenuation, the dioxane problem, well, maybe it's not quite as bad as we'd guessed without all these data. But next, let's look at the potential impact of matrix diffusion on dioxane fate and transport. Mm-hmm.
Sure. Now, we know that matrix diffusion, it's a big issue for chlorinated solvents based on some great recent research, a lot of it sponsored by CERDIP and ESDCP. This issue can really enhance the persistence of these compounds. This diagram illustrates a few of the reasons why. So if you think about an aquifer overlying a low permeability zone, something like a clay or a silt where there's little advection, you may have a source being released up there in the high permeability or transmissive zone. While that source is present, you see a loading of that adjacent lower permeability zone based on diffusion processes. So contaminants are moving based on a concentration gradient, pushing material via diffusion into that low K zone.
So once that source is depleted, you've essentially reversed the concentration gradient. And now all that mass that is diffused into the lower K zone, it has the potential to back diffuse into the aquifer and sustain the dissolved plume for a long period of time.
So in the CERDIP project, we attempted to model a typical dioxane release scenario to see what would happen.
And this was accomplished using the Matrix Diffusion Toolkit, a free software tool that was developed for ESTCP by Colorado State University and GSI. Dr. Shella Farhat at GSI was the principal designer of this tool.
So in this particular case, we wanted to simulate TCA and dioxane being released at the same time. We had to define a loading period and representative concentration during this loading period. And we started it out in 1970, and we found out that dioxane essentially depleted from the high permeability parts of the source zone within 3 years, basically because it's so soluble, but that doesn't mean it's gone from everywhere. So to show what happened, we put together this little movie. So Chuck, if you get your popcorn, get ready and I'll hit play.
You know, I guess I forgot the popcorn, but don't let that stop you. Mm-hmm.
So here's our modeling domain. We're looking at a 2-layer model with sand on the top and our low-K silt or clay below. We have depth on our y-axis and distance down gradient on the x-axis. So we're going to release this source up in the transmissive layer. And remember that for dioxane, this really only lasts for a few years.
Now, what we're really interested in, what happens in that low K zone. While the source is present, you get diffusion in, and when the source is absent, you get diffusion back out. We have our color-coded key for concentration down on the bottom. High concentrations are red, and we can also track the percentage of mass in the low K zone on the bottom right.
So our release starts off in 1970, and we'll show what happens for 80 years. Right away, we see a huge amount of mass, those bright reds being pushed in the low K zone. We're already up to 1988, and we've got more than 70% of that mass in the low K zone. So a few obvious things going on here. Even though the source was gone in 1973, there's still a significant concentration gradient that pushes mass deeper into the low K unit. Secondly, even though the source on the left-hand side was depleted pretty quickly, you saw that remnant move down gradient to the right and contribute to diffusion into the low K zone as that plume expanded. And if you were keeping track of that number in the lower right, the mass in the low K zone, it jumped up pretty quickly, but then it didn't really change all that much. Mass diffusing out, maybe near the source zone after the source was gone, that was being balanced by mass diffusing in farther down gradient. So in terms of the mass in the low K zone, we're seeing a pretty stable situation, even 80 years after the release. Still a lot of red in that source zone. Those are concentrations above 100 milligram per kilogram, and yellows throughout an area 300 meters down gradient and 2 meters into the clay.
Okay, so clearly this could enhance the persistence of dioxane plumes. You think this is a concern at most sites?
Well, there's definitely a sense that the geology at sites is a lot more heterogeneous than we maybe originally assumed. So that's what's shown in this example of a hydrostratigraphic profile from the hydraulic profiling tool, where you've got getting an estimate of the hydraulic conductivity as you advance this tool deep into the ground. You can see that there's a lot of heterogeneity in the permeability, and these differences in permeability can lead to a lot of mass storage. This is really important because it's less practical to attempt aggressive in situ treatment if a site is dominated by mass in the low K zones. Now, we've seen the evidence for this at some sites, although it's not universal. This project specifically documented that there's a lot of dilute dioxane sites out there, suggesting that there's no real source zone left, but maybe the source is the mass diffusing from these more stagnant zones at these types of sites. At any rate, at a minimum, I think that matrix diffusion does need to be investigated and included in site-specific conceptual models.
Okay, sounds good. So let's wrap up by revisiting our key points. We saw results that suggest that there's some good news in terms of dioxane plume sizes.
Yeah, and the implication of this is that maybe it's less likely that the dioxane plume extends way beyond the existing monitoring network that was probably designed only for chlorinated solvents.
And also there's evidence for attenuation of 1,4-dioxane at these sites.
Right, and that enhances the viability of M&A and biodegradation-based remedies.
And finally, we also saw that matrix diffusion can be an important consideration in how the site's managed.
Yeah, and so when you think about these collective results in terms of an improved conceptual model, they do suggest that at some sites, conventional treatment may be less feasible, and other strategies like natural attenuation through biodegradation or even containment might be more appropriate options for longer-term management of dioxane.
Okay, well, thanks, Dave. Now here's where you can find more information about this great CERTIP project on dioxane. And remember, this is just one of a number of videos highlighting key results from different CERTIP and ESTCP research projects. Just go to YouTube and search for CERTIP ESTCP micro lectures to see more of these.